right, so we want to look at some useful mathematical relationships, specifically in spherical and polar coordinates. And what we're going to do is derive some relationships that will be useful for when we do integrations involving surface area elements and volume elements. And the derivations and justifications for the formulas that we're going to look at all hinge on this idea of arc length. Okay, so just a refresher, when you have a radius of a circle, you have the center and you have two radii that make an angle theta. Okay, the length along the perimeter that the two radii subtend is going to be called the arc length. And your arc length and the radius of your circle and the angle theta are going to be given by this formula. All right. So theta or S is equal to theta R. And I apologize. So S is equal to R theta. And if I have a very small sliver of angle, okay, so I haven't changed my R at all, but I have an infinitesimally small sliver of angle, then this is going to subtend an infinitesimally small arc length ds, okay? And you can see the relationship that would hold here. If I take the differential of S, I get ds, and then I would have to take the differential of the right side, and since R is constant, it doesn't get differentiated, but theta can change. So I would have ds is equal to rd theta. So this is known as the differential arc length. Okay. Now, as a simple exercise to kind of get warmed up for what we're about to do, I should be able to integrate I should be able to integrate both sides, and I should find the formula for the circumference of a circle. If I go all the way around the loop, okay? So I'm going to go all the way around the loop. And if I do that, then my limits of integration would be from 0 to 2 pi, since there's 2 pi radians in angular radian measurements around a circle. And the integral of ds is just going to be S, the total arc length. Well, we could write this actually. Let's write it like this, because the total arc length around the circle, right, would become the circumference. So I would have C on this side, and this would give me R times theta from 0 to 2 pi, which would give me R times 2 pi, which gives me 2 pi R. Okay? So you can recover the formula for the circumference of a circle. Now, you don't have to integrate this, okay? You don't have to. You can use this formula right here just by saying, okay, if I go all the way around the circle, then my arc length is going to be the circumference. And if I go all the way around the circle, then my angle will be 2 pi. Okay? But you can do it from the integration, and you get the same answer. All right? So, But again, everything that we're about to do hinges on this idea of arc length. That arc length is equal to r, the radius of your circle, times a angle. Okay. So if I have, moving into 3 dimensions, if I have a sphere, okay, what we're going to do is, first things first, we're going to let now this is a quarter of a sphere, okay, this is not a whole sphere. This is a quarter of a sphere, and what we're going to do is, first of all, r is going to be the radius. Theta is going to be the angle measured from the positive z-axis down. Okay, so theta is measured Okay, so theta is going to be measured from the z-axis toward the negative z-axis. Now, a lot of math books, this is where mathematicians and physicists kind of butt heads sometimes. And a lot of mathematicians will reverse the roles of theta and phi, but it doesn't really matter, right? As long as we keep them straight amongst ourselves, then things should be fine. And phi gets swept from the x-axis around the xy plane. Ooh. So, with this in mind, if I have a surface area element dA, okay, now my area element is going to be, let me label them length 1 times length 2. Okay, so dA is going to equal length 1 times length 2, the sides of this box, right? Now, what is length 1? So length 1, this side right here, let me do a little bit better job. And in fact, let me do it in a different color perhaps. Okay, so this side right here, okay, is an arc length of width d theta, and we're at the surface of the sphere, so we have a radius r. So this arc length along the surface is going to be r d theta, and that's where this comes from. Now, length 2 is a little bit more complicated, but if I put the projection of length 2 down in the xy plane, it subtends this angle d phi. Okay, so part of this will have length d phi, or angular displacement d phi, but it has a straight line length from the z-axis of r sine theta. Okay, so this length right here is r sine theta from this triangle right here. Okay, and so if I kind of look at this from the top down, okay, if I look at this from the top down, draw a circle, and so yeah, I actually don't want to go out to the edge. So imagine I'm looking at this dome from the top, and I see a surface area element like this. Okay. So this length here is going to be r sine theta, and the width is d phi. Okay, and so the total length is going to have an angular, the arc length is going to be the radius r sine theta times the angular differential d phi. So this is going to be r sine theta d phi. Okay? So, and the reason that you use r sine theta here instead of just r, okay, because this arc length right here is stretching across the sphere directly across from this point on the z-axis, not from the origin. Okay? And as a result, the arc length or the radius for this arc length right here is this arm right here, r sine theta. Okay. So if you want to look at this from the side, so if I were to draw the whole sphere from the side, then this would be like this. My surface area element is hanging out here. Okay. And so here is r, here is theta, and here would be r sine theta. Okay. Let me actually... Okay. So this arm is what is extending out this way. All right. So my dA, my area element dA, is r squared sine theta d theta d phi. All right. So that is my area element for the surface of a sphere. And now what we want to do is integrate this and obtain the total surface area of a sphere. Okay? But we have to know our limits. Well, theta, as I said, will stretch from the z-axis, and it will stretch all the way down to the negative z-axis. So if I go 180 degrees, that is effectively going from 0 to pi. So the limits of integration on theta are going to be from 0 to pi. And your limits of integration on phi is just going to sweep around the entire xy plane, and so it's going to go from 0 to 2 pi. Okay? And so, if I integrate both sides, my area... Now this is going to become a double integral because I have two differentials. So this is going to be r squared times the sine of theta d theta from 0 to pi. Ooh, that's a terrible integral sign. Times the integral of d phi. All right, and this is going to be from 0 to 2 pi. And so we're going to have a is equal to r squared. Now, the phi integral is going to be the simplest because this just turns into 2 pi. Right? Because this turns into phi evaluated from 0 to 2 pi, which is 2 pi minus 0. So this just becomes 2 pi. Okay. So I'm going to go ahead and put the 2 pi out here. Now, the sine integral is a little bit more complicated because this becomes negative cosine evaluated from 0 to pi. And this is equal to negative cosine of pi. Well, cosine of pi is negative 1, right? And negative 1 with a minus sign is 1. So this is negative cosine of pi minus negative cosine of 0. So negative cosine of pi becomes 1, and cosine of 0 is 1, and the negative signs cancel each other out, so this is just 1 plus 1, this is just 2. So I have r squared times 2 pi times 2. And so the result is often written as 4 pi r squared. So this is the surface area of a sphere, okay, 4 pi r squared. And so if you know what the radius of your sphere is, you know what the surface area is. And if you're in SI units, then this would be in square meters, right? And so basically what this means is if you have like a flexible measuring tape, and you could stretch it across the sphere in different ways and measure the area with an actual instrument, you would get this value, right? You would get 4 pi r squared. All right, so the volume element is actually very, very similar. The only thing is we don't let the radius be fixed, but we let the radius change as well. So the way we do this is instead of drawing a surface area element on the surface at a fixed radius, we draw a box with a finite width. So this width right here carries length dr, but the other sides of the box are the same. This side of the box is going to be r sine theta, and this side of the box is going to be this side of the box is going to be r d theta. I apologize. Whoops. I meant to do this. And actually, let me use different colors here. So this side of the box is going to be rd theta, and this side of the box is r sine theta d phi, just as before, but now the box has thickness dr. Okay, so the volume element is going to be rd phi, or rd theta for this side times r sine theta d phi and then that's going to be multiplied by the thickness dr, right? So putting this all together, this is often written as r squared sine theta dr d theta d phi, right? And when you're integrating over the volume, your theta and phi limits will be the same, but r will now stretch from 0 to the total radius of the sphere if you're integrating over the whole sphere, right? So this is the formula that we use to get the entire volume of a sphere. Okay, so if I integrate this function over the entire surface of the sphere, or I'm sorry, over the entire volume of the sphere, using the limits that we just had, then what we will do is achieve the volume of the sphere 4/3 pi r cubed. So if I and again, now this is a triple integral because I have 3 differential elements. So I need to break this up into 3 integrals. And for those who might not have seen double and triple integrals before, the way you do a double integral is just like we did over here. So you can keep all of your functions or expressions that have to do with the same variable under the same integral sign. So you can separate your total expression out into the parts that only depend on the same integration variable. So anything that would have to do with theta would go in this integral. Anything having to do with phi would go in this integral. And same thing with triple integrals. So I want to put my r squared and dr together. And then I'm going to integrate my sine theta d theta. And I'm going to integrate my d phi. So my limits of integration on r are going to be from 0 to the radius of my sphere. Once again, theta is going to go from 0 to pi, and d phi is going to go from 0 to 2 pi. And we've already done this integration. We just did that in the last slide, and we already saw that this goes to 4 pi. Right? So I won't repeat that procedure, but integrating the first integral here is going to give us, let's do it formally. So this is going to give me r cubed over 3 evaluated from 0 to r. Okay? And that is going to give me r cubed over 3 minus 0, which is r cubed over 3. And so when I join that together with the 4 pi, that gives me the 4 pi thirds r cubed expression that is the volume of a sphere. Right? So, and perhaps, okay, I'm not completely happy with this. Let me see if I can explain this just a little bit better. I think I can do a little bit better. Imagine, okay, this arc length right here is part of a circle that subtends around the sphere like that, right? So if I draw this circle right here and let it go all the way around the sphere, that would give me a circle whose radius was r sine theta. So then when I have an arc length across that, that arc length would have angle d phi associated with it. And so the arc length across is going to be my radius r sine theta times my angle d phi, right? So that arc length would be r sine theta d phi. Okay, so hopefully that's clear. But these are your elements, okay, for spheres. We're going to use these quite a bit. So I encourage you to look at them and study them, all right? And so let me do one more quick thing here, because we're going to use cylinders quite a bit. Now, we're not going to go through how to define things in cylindrical coordinates, but what we will do very quickly are look at a couple of formulas for the surface areas, and if I can draw straight, of a cylinder. Right? So imagine this is a perfect cylinder. I know it's a bit of a stretch with my artwork, but let's say this cylinder has a height h, and the circular face has a radius r. Okay? So let's start with the surface area. Right? Well, the surface area, you have two circles, one here and one here. And so the surface area is going to equal the areas of the circles plus the area of the tube. Okay. And so the areas of the circles are going to be, the area of a circle is pi r squared. And this is capital R, since we've defined the radius to be capital R. And we have two of them. And then the area of the tube is a little bit trickier to think about, but if I think of this tube, let's say that this is something like a paper towel roll or a toilet paper roll, okay? And if I cut that toilet paper roll with scissors down like this, and I stretch it out and I roll it out so that it's flat, then I would have something that looked like this. Right? So this would still be h, this would be the height, and the length here would be the circumference of the circle. Right? Because I would be stretching this out and rolling it out, so this would be 2 pi r. And so then the area of this rectangle is 2 pi r h. Right? So that's the surface area of a cylinder. And then the volume of a cylinder is going to be length times width times height, right? But what you can think of, this is the top is a disc, right? And if you think of the disc having infinitesimal widths dz, so we typically think of the disc as being flat in the xy plane and extending down, and the tube extends down into the z direction. So this would be dz. then the volume of this infinitesimally thin disk, okay, the volume of this infinitesimally thin disk would have volume element dV would be equal to pi r squared dz. And if I integrate that over z from 0 to h, just over the length of the tube, then the volume is pi r squared times h. Okay, so that is the volume of a cylinder. And actually, while I'm thinking about it, I'll do even one more yet. So this kind of goes back to the circle. And so imagine that I have a circle. Oh boy. I'll tell you what, let's do it this way. Let's see how well I can draw a circle. Okay, that's a pretty good circle. We'll use that. Okay. And so let's put center of the circle right here. And I want to find the area of this circle. So I have a surface area element on this circle that looks like this. Okay. So the radius of the circle is going to be r. And my surface area element here is going to stretch at a distance r. Okay. And actually, let me do it this way. Oh, that's terrible. Okay. So these are both r, and this is a width dr. Or I'm sorry, this is a width d theta. So this arc length here is going to be lowercase r d theta. And this length, since it's along the radial direction, is just going to be dr. And so my surface area element for a circle is going to be r dr d theta. Okay? r dr d theta. And if I let r go from the origin to the radius of the circle, and I let theta go all the way around the circle from 0 to 2 pi, then integrating this should give me the area, the total area of my circle. And in fact, this is where the area of the circle comes from. Okay. And so we know what rdr, the integral of rdr is. It's r squared over 2. And this is from 0 to r. And this is going to be multiplied by the integral of d theta from 0 to 2 pi, which just gives me 2 pi. And my result is r squared over 2 times 2 pi, and my 2's cancel, and I get pi r squared. All right? So that is a little bit about area and volume elements and how we can use them to derive the relationships of things that are going to be useful to us. Okay, so with that in mind, we will see you in the next video.